Okay, so hello everybody. I am now recording the rest of the denaturation and functionality lecture, which will be on your exam next week. So we didn't get to finish it last Wednesday. So today is Wednesday, March 12th. So I'll try to finish the lecture. We'll see how long it takes. And based on how long it takes to finish it, we may not have a lecture after your exam on next Wednesday. So I will, at the end, I look at the time and then we'll confirm whether or not you will have a lecture after the exam next week. So I will also send you an email about it. Okay, let me share my screen. Um, so, okay. So I should be sharing the correct screen here. Okay, so basically, we talked about this last time, so I will move on. You have the recording. I put it on Canvas. So now we want to talk about effect of temperature on solubility. So we talked about effect of pH and salt, and now we'll talk about effect of temperature. When the temperature increases in general, the solubility of the protein increases because you have more thermodynamic and more interactions with water. And this is true up to a certain point until the protein starts to denature. Once the protein starts to denature and form protein-protein interactions, then solubility goes down. However, there are always exceptions of the rule. So here we are showing an example. Beta-casein is the most hydrophobic protein in milk, and it actually is most soluble under refrigerated conditions. So it actually in milk, if we put the milk in the refrigerator at 4 degrees C or around that, what happened is some of the beta casein they leach out of the micelle into the soluble whey fraction. The reason they do that because beta casein is very hydrophobic, most hydrophobic casein among the other caseins. You have the alpha S1, alpha S2, kappa, and beta. Beta casein is the most hydrophobic, and within the micelle, it interacts via mostly hydrophobic interaction. And if you remember, when you're studying, you will remember that the hydrophobic interactions actually weakens with lower temperature. So they're going to be weakened with lower temperature, so the beta casein will leach out of the micelle and becomes a little bit more soluble in the whey fraction. So that's the exception here. And this just reminds you that temperature also impacts hydrophobic interactions, and at lower temperatures, hydrophobic interactions are weakened. Okay. How to measure solubility? Most of you have done this before or familiar with the concept. What we do to evaluate the solubility of the protein is we prepare a protein solution at specific protein concentration that is relevant to a particular application. So you can prepare 1%, 2%, or often in our lab, we prepare 5% protein solutions just because it resembles what a high protein beverage would have in terms of protein concentration. And if you want to put a protein claim, you should have at least more than 4.2 grams of protein per 100 milliliter that is available protein, bioavailable protein. So we prepare it mostly at 5% protein solution. And it's more meaningful to evaluate at relevant protein concentration rather than very low protein concentration that are not relevant. In fact, I think in the class I mentioned, okay, sometimes I look at a paper and they claim that, oh, protein solubility is great or got improved after certain treatment. And I look at the concentration and they prepare like 1 milligram per ml, which is 0.1%. We're not relevant at all. So we prepare a protein solution and we usually let it wet for a while, disperse for a while, so that we make sure that the protein is well dispersed. And if it's going to form a true solution, it has time to form a true solution. We let stir 1 to 2 hours, and then after we make sure that it's well dispersed, we take aliquots. Sometimes we prepare the solution in a buffer or at a particular salt concentration if we want to look at the impact of a specific stabilized conditions. In our lab, what we do is we don't necessarily use a buffer. We adjust the pH either to neutral or to an acidic pH that we're really interested in, that would be relevant to an application like acidic beverages. So we measure at 3.4 and we do also at neutral pH. So we adjust the pH and we also make sure it stabilizes at the adjusted pH. And then we take aliquot of, and then these aliquots, so we measure the protein in the aliquots before we centrifuge, so we know how much of the protein is actually present in the system. So we vortex, we make sure we take a representative sample, we measure the protein, and often we do that with a nitrogen combustion method or Keldar, but Keldar is lengthy, so we do nitrogen combustion using our LECO. And what happens is after you vortex, you determine the measurement of the total nitrogen in your sample. Then you take that tube, microcentrifuge tube usually in triplicate, and then you centrifuge. And then we take the supernatant and we measure the protein in the supernatant. And what we do is to calculate solubility, we take the amount of protein in the supernatant percent over the percent of protein in the original initial before we centrifuge, and we get the relative protein that remained in solution, and that would be representative of the percent protein that remained soluble. And that's how we do that. We could do calorimetric assay, but we want to make sure that there are no interfering substances in our sample that might absorb at the same wavelength or maybe interact with the reagents and give us false protein concentrations. So that's why a recommendation is a nitrogen-based assay. So either a Keldar or a DUMAS. I just realized that this is spelled wrong. There is no N here. Let me make sure I have a pointer. Pen here is what I want. So we don't have N. DUMAS. Okay, so next, I want to talk about gelation. So formation of a gel. The gel is a continuous 3D solid-like matrix or network of protein embedded in an aqueous solvent. So meaning you put the protein in aqueous and then you induce gelation conditions. It could be thermal, it could be acid induced. So you induce the gelation conditions and then a gel is formed. And when the gel is formed, it's entrapping water. So, and we have so many different forms of gels. This tofu is a gel. This hot dog is a gel. The jelly is, of course, a gel. And even in here, the egg white is a gel. Also, you might be surprised that I tell you, well, yogurt is a gel as well. It's a just different type of gel. Gels don't necessarily have to be really hard, solid matrix or tough texture. It could be anything as long as you form a 3D network that actually entrapped water. that's a gel. You form the gel. So the water is dispersed in the or immobilized in this gel matrix and or held. So that's when I say, water holding capacity. It relates to the amount of water that's actually held physically entrapped within this 3D network. And different types of proteins form gel at different concentrations. So we can form a gel with as low as 1%, and that would be gelatin. Gelatin is the protein that is, the best forming gel protein because it forms gel at really low concentration. And whey protein, for example, also gels at low concentration, like 5%. But pea protein, for example, depending on the source, it might not form a good gel unless you have 20% protein. Soy, it can form a gel at 12.5, but usually we form it at 15 so that we can actually measure the gel strength. So different proteins gel at different protein concentrations. So how does the gel occur? So first of all, in formation of a gel, it is essential that the protein denature in some way so that we have exposed reactive groups, hydrophobic groups, sulfide groups, free sulfide groups if they are present. So what happens is once we induce protein denaturation, we can also induce protein-protein interactions. So the conditions, though, are essential so that instead of forming an aggregate and precipitation, we induce slow formation of that protein network. So the conditions should really start with you have your solution, proteins diffused or forming through solution or dispersion at least. The better the solution, the better is the protein formed as a true solution, the better characteristics of your gel. The smoothness, no grittiness, uh, it forms a more, what do you call, as systematic or a homogeneous gel is the word I was looking for. So, okay, so you have your proteins diffused, interacting with water, you induce this denaturation, and slowly the proteins start, forming what we call soluble aggregates. So then these soluble aggregates start forming larger network of proteins interacting with each other. And as that larger network is starting to form, then we entrap the water. So here, for example, you have an area where water is entrapped. Okay, so I didn't mean to do that. I don't know why it does that. But here entrapped water, and then more polymers are forming, and then water is physically entrapped, and the gel is formed. Now, the protein can be denatured by heat, by pH, by high pressure homogenization that you could lead to an denaturation potential formation of the soluble aggregate to increase the viscosity, and then you form that gel. So most food gels are thermally induced. Now, it accepts few exceptions like yogurts. These are not thermally induced gels. These are by acid, induced by acid. Okay, so this we have thermally irreversible, very common, and usually an example of that is this egg white. So it's thermally irreversible because once the protein denatures and start forming interactions, some interaction will be really, really strong, like strong hydrophobic interaction or disulfide linkages. So this happens when the protein is large in molecular weight and have a lot of hydrophobicity. So, for example, over 30% of your amino acids are hydrophobic, and you have high degree of sulfide groups, like in egg proteins, then you're forming a gel that is irreversible. Now, in other situations, you can have thermally reversible gels, and this is very unique type of gel. And an example is the gelatin-based gel. So you have the native collagen, they're mostly stabilized by hydrogen bonding. Hydrogen bonding are weakened with heat. So as you heat, you are really denaturing the protein. Hydrogen bonding are broken, and then when you cool, and then hydrogen bonding starts forming because lower the temperature, you start forming these um, hydrogen bonding again, and then you will form that gel. So it's reversible because heated again, you break these hydrogen bonding and then it becomes solution. Cool it, it forms a gel. But you cannot go back to the native collagen. Once you form that gelatin, the denatured form of collagen, that's it. But yeah. Okay, so to form a gel, you really want to have that balance of attractive and repulsive because you don't want to have really strong attractive interactions. You really get aggregation at that point. A lot of protein-protein interaction, attractive interaction, a lot of less protein-water interaction, and you don't get that nice network and entrapment of water. So what happens, you have your native protein in solution, you apply heat, the protein unfolds, give it more time, and the protein starts forming this interactions. You reach gel point, and the matrix, you give it more time, and the matrix is formed. Usually, what happens is when we prepare our protein solutions at the concentration that we know that it will form a gel, we again wet it, put it in solution, let it stir and disperse well. And if the protein forms a true solution, give it time to form true solution. Then we heat. And when we heat it for a specific period of time, also test it for the type of protein and the concentration of protein that we have. And then we take it out, we let it cool, and the gel sets. And we get to this, our equilibrium matrix. All right, so a lot of properties affect gelation. First of all, molecular weight, properties of the protein itself. So the molecular weight. So the larger the protein is, and if it forms a true solution, you get more gel network formation at lower even protein concentrations. So high molecular weight but soluble protein will give you better gelation properties. If the molecular weight is really small, like in hydrolyzed system, protein hydrolysis, if we have most of our hydrolysis or the peptides in the hydrolysis are less than 10 kilodalton, chances are low to form a gel. Composition is important, so the degree of how much percentage of what's the percentage of hydrophobic amino acids, presence of disulfide interchange, potential hydrosulfide groups, and potential formation of disulfide, and also charge. Too much charge, a lot of negative charge or a lot of positive charge will cause more repulsion than attraction. So you really want that balance. You want to have protein interacting with water, but you don't want them to repel each other too much to an extent that we don't really form that network. So it's a very important factor as well. So hydrogen bond, electrostatic interactions, they weaken as temperature increases. So they also lead to protein denaturation with unfolding, and hydrophobic interactions are strengthened. Okay, so we have to remember that. So it's kind of like bring the proteins together via hydrophobic interactions, and when they are in close proximity, if there are free sulfide groups, then disulfide interchange happens and stabilizes that gel matrix. And disulfide interchange is stimulated by temperature as well as pH. So neutral pH or a little higher stimulates disulfide interchange. Sometimes when you have a mix of different proteins with different characteristics, you form stronger gels. So if you take, let's say you have a pure form of beta-lactoglobulin and a pure form of alpha-lactoglobulin, whey proteins. Alpha-lactalbumin alone doesn't form a strong gel. It doesn't have a free sulfide group. So you need a free sulfide group there to initiate disulfide interchange. It does have disulfides within the molecule, but if you don't have a free sulfide group like beta-lactoglobulin have, you don't have that trigger of forming disulfide interchange. And then another thing that an application like yogurt, for example, they add sometimes whey protein isolate to yogurt formation to enhance the gel matrix and also prevent syneresis over time. So enhance the water holding properties. So what happens is kappa casein has sulfide groups, disulfide linkage, not a lot, like maybe one per molecule. And then you have whey protein, beta-lactoglobulin with a free sulfide group. So when you add it, so the beta-lactoglobulin is going to interact with the kappa casein and also enhance the gel matrix formation, increase protein-protein interactions. Okay. pH, protein concentration, pH, and salt, and definitely impact protein gelation. We talked about concentration. So a protein concentration is important based on the type of protein we start with. Some proteins can naturally form strong gels based on their molecular characteristics and require less concentration to form the gel. Other proteins require high protein concentration to form a gel. So the pH, what happens at extreme pH, you have a lot of net charge causing repulsion. So the protein stays in solution. If your pH is close to the isoelectric point, so you have this gel forms but gritty, a lot of turbidity because you have less charge, less interaction with water, more protein interaction. You form a gritty type of gel. So you really want to find that sweet spot for proteins to form a nice gel that is strong enough to maintain its structure and it's not gritty and not too soluble in water, and the protein water interaction is high, so the protein never forms a gel. So you want to find this very nice sweet spot where a gel can be formed with desired characteristics. The salt acts in a way similar to the salting in, salting out effect. You really want to make sure that a protein is a true solution. So sometimes a little bit of salt helps the protein to be in a true solution, enhances its solubility, which potentially gives positive gel characteristics, formation of gel. But however, a lot of salt, which causes salting out, causes grittiness and aggregation rather than a nice 3D texture. Calcium ions, they are divalent ions. So because they are divalent, they can form bridges. So often when we're forming tofu, for example, calcium is added to enhance protein-protein interaction. So at neutral pH or above the isoelectric point, the protein carries negative charge. So there are a lot of negative charges. And if you have a divalent ion, that calcium can interact with one protein here, and another, the other positive charge can interact with another protein, and then it forms that bridge. So it enhances gel formation. And that's why when we're making cheese as well, sometimes we add calcium to enhance the curd yield so that we have more curd generated and we don't lose caseins with the whey or have less curd yield. Heating temperature and heating rate. So we really need to heat to reach the denaturation temperature of the protein. So if we heat at 70 degrees and the protein denatures at 80, or 90, we're not really, unless we increase the time, we're not really encouraging the protein-protein interaction. So we need to induce denaturation, and we need to make sure that the heating is, the rate is not too high. If the temperature is really high and the protein solution is increasing in temperature very quickly, what happens is protein-protein interactions and aggregations happen very fast. So it becomes a really fast process leading to protein precipitation rather than the slow denaturation and coming together, forming soluble aggregate, and then forming a nice network and trapping water. So heating temperature and heating rate is very important. Proteolytic enzymes are undesirable, obviously, because they're going to chop your proteins and they will not form a gel. One common example I always give is if you want to make a jelly and you really want pineapples in this jelly, don't use fresh pineapple. Go get a canned pineapple and use it because of bromelain enzyme naturally present in pineapples. So bromelain is a protease. So if you just want to get your jelly mix and put fresh pineapple, it will never form a gel. So that's another example I always give. So let me see here. Protein concentration. Oh, the last bit is polysaccharides and sugars. Sometimes presence of polysaccharides interacting with water, with protein can help protein water interactions, can help with forming holding water and forming a nice gel matrix as well. So polysaccharides and sugars play a role also in holding water and trapping water within the gel matrix. So here are examples of molecular weight and impact of molecular weight. This based on research we have done in the lab. So here we have soy protein. Soy protein forms really good gel relative to other plant proteins we have tried working with. So this is a camelina protein that we extracted under different conditions. So soy protein has twice as much of gel strength at 15% protein. Even, I don't remember now if we had to put camelina protein at 20% protein to form a gel. So looking at the molecular weight of camelina protein compared to the molecular weight of soy protein, so the functional subunits of camelina are of lower molecular weight than the functional subunits of soy protein. So having this higher molecular weight is one of the positive characteristics that make soy protein interact better and form a gel. So, but it's not the only factor, obviously. There are other factors, but this is one example of molecular weight impact. Now, we look at soy protein and pea protein. Pea protein is very related to soy. It's a legume protein. It has viscin and legumin, so 11S, 7S proteins. So the glycine in soy is under similar class to legumin, and both are 11S based on sedimentation coefficient. But soy forms a better gel, stronger gel at lower concentration. So here, actually, it formed gel at 10%, but very weak. Pea protein does not form a gel at 10%. Soy forms a really strong gel at 15%. Pea does form a gel. Some of them do, some of them don't, even depending on the source. If they form the gel at 15%, it's really weak, and we cannot even measure texture properties. So then when we say, okay, they both have high molecular weight proteins, but why are they that different? They're different because they differ in the composition of the proteins, the different functional proteins. So legumin is of much less ratio compared to viscin proteins. And whereas in soy, you have more of that 11S than the 7S proteins. So what does that mean? It means this glycine in soy and legumin in pea, they are more they form stronger gels because they have disulfides in them and sulfidyl groups that will initiate disulfide interchange. So in pea we have less of that, and even legumin in pea has compositionally less cysteine than the glycine in soy. So not only molecular weight, here are characteristics of different proteins within similar or related species. And here are examples of different types of protein. Whey protein is not a large molecular weight protein. It is 18 kilodalton for beta-lactoglobin and 14 kilodalton for alpha-lactalbumin. However, um, it forms stronger gel at a lower concentration than soy protein. Why? Because of its disulfide interchange and this sulfide group, free sulfide group in beta lactoglobulin that really helps. And it also denatures at lower temperature than soy. So this characteristic, although not higher molecular weight, the specific characteristic of the protein, and it's a very soluble protein as well. So it gives this very good balance of protein-protein interaction and protein-water interaction, giving you a stronger gel. And then, so we go from whey being stronger to soy, to fava bean, to pea protein. It's also almost kind of like a paste more than a gel. And rice protein does not form a gel, even at above 20% protein. So, yeah. So in an application, what does that mean? So, we are trying to get, or companies are trying to replace animal-based proteins in different application, and one of them is dairy alternatives, so cheese. So plant-based cheese. So if we look at plant-based cheese composition compared to natural cheese, and this is CLSM, confocal light scanning microscopy, CLSM, with staining. So the green is staining protein, the red is staining fat, the blue is staining carbohydrate. So what we're seeing here is natural cheese. You have this green matrix. So this is the nice protein-protein interaction gel-like matrix that is entrapping the fat within your cheese. So you have this nice matrix. If we look at the vegan cheese, we see a lot of blue, and the green for protein is like dispersed. It doesn't form a network. And the fat is kind of dispersed as well. But this blue tells us that in vegan cheese, you have a lot of hydrocolloids, a lot of carbohydrate, starch, and very little protein. And the protein is added just, they have protein in there, but it's not really for formation of that gel because it doesn't form that nice gel and entrapping the fat in this case. So that's why vegan cheese is very different compositionally than dairy cheese. We measure gelation, but using different approaches. So we first form a gel under specific conditions: pH, protein concentration, temperature, time, rate of heating, all of that. And then once the gel is formed, we measure water holding capacity. It tells us how much the gel was strong enough to hold water. So usually you get the gel, you form it, you turn it upside down and measure how much water is lost due to the gravitational force. And then another thing we if we want to measure that water holding capacity using an actual application, it can be done. So in here, we did in one study trying to look at formation of beef patty using whey protein as a supplement that we add to enhance the holding of water and fat. So we prepared patties with whey protein and without. And the way we do it is we put a certain amount of meat composed with or without whey protein in this case, and we cook it and we let it settle, and then we see water and oil separated, and we measure the amount of water loss and oil loss with and without the protein. So that is measurement of water holding within a food gel matrix. So we have the model system where you just put protein in water, and you have the actual system that you're trying to measure the impact of ability of that food gel to hold water. Okay, so then once the gel is formed, we can do rheometry on that, measure shear strain, shear stress, or we can measure the strength of the gel by using a texture analyzer. And under specific conditions, speed, and using a specific attachment, and then we record the weight that took to kind of smush the gel, and we convert the weight to force, to Newton. Okay, so moving on to emulsions and foam systems. So basically here you have two phases with a lot of surface tension. So you get separation, whether it is aqueous and fat or aqueous and air. So you have high surface tension, and if you want to stabilize such systems, you need to work it, homogenize, and have something in that homogeneous mixture that would stabilize your emulsified system or foam system. So we always, in an emulsion, for example, or foam, you have the continuous phase or dispersing phase, and you have the dispersed phase. So in emulsion, the continuous phase can be water, and the dispersed phase can be oil, or the dispersing phase can be oil or fat, and the dispersed phase can be water. So, for example, butter. Butter, you have the dispersing phase as fat and the dispersed phase water. And so if the system is liquid, usually it is an emulsion. It doesn't have to be really liquid. Sometimes an emulsion is like a gel with fat is an emulsion system. But if you are trapping bubbles, then this would be foam. So, but the concept is with proteins as stabilizers is that when you have protein and you apply, you homogenize, you mix, you homogenize. So that protein goes to the interface and it unfolds, orient its hydrophobic components to the oil or to the air phase, and its polar component to the aqueous phase, whether it's continuous or dispersed. And the proteins start forming a film around the bubble or around the oil or around the water if the water is dispersed. So that's basically what I just said, is anchoring its hydrophobic and hydrophilic to the correct phase, basically. So You can form temporary emulsion by just homogenization. So you can break, if let's say it is water and oil or in water, so you break the droplets by homogenizing them, and the more you put work into it or force into it to homogenize, the smaller are your droplets, and you will form an emulsion. But if there's nothing to stabilize the emulsion, you get phase separation. Basically, this is what here I'm illustrating, and also here I'm illustrating the importance of homogenization. So you have to put work so that you reduce the surface tension and increase the surface area with the difference in surface area. So basically, we are trying to get smaller and smaller droplets. The smaller the droplets, the better the stability. And then we can use protein, obviously, as stabilizer, or you can add emulsifiers, small molecular weight emulsifiers, like lecithin or diacylglycerol or monoacylglycerol that will act as stabilizers as well. So here we're illustrating a protein emulsifier where if the protein here in this case, you have a protein with a lot of hydrophilicity, and this hydrophobic is mostly concentrated in the center, and the protein is not denatured, so you won't have adhesion at the interface. And then if you have a little bit of hydrophobicity, you might get some adhesion, but not that great. But if you have a balance between hydrophobic and hydrophilic groups at the surface, that's why denaturation of the protein enhances emulsification, then you get adsorption at the interface. So this is very important. You need a balance between hydrophobic and hydrophilic groups on the surface of the protein. That's why partial denaturation is often something that we do to enhance emulsification. So this is an illustration of the various processes that happens during the formation of an emulsion or a foam. So you get your protein, it goes to the interface between the two phases, it unfolds and reorientates its components, and then it starts forming protein-protein interaction. That thin film starts to form at around the bubble or around the oil droplet or water droplet that we formed with homogenization or mixing. So these are the steps: going to the interface, absorbing at the interface, unfolding and reorientating its different components, and then forming protein-protein interaction, that film around the bubble or the droplet. Okay, so we have intrinsic factors that impact emulsifying properties and extrinsic factors. Among the intrinsic factors, surface hydrophobicity is very important, but not only surface hydrophobicity, it's the balance. Again, it's very important. Balance of hydrophobic to hydrophilic components, flexibility. So how well the protein is able to unfold and be flexible so that it reorientate its components and start forming that film. Charge. Excessive charge, we won't form the film. No charge will form aggregates, so we need to find also where the protein carries sufficient charge to interact with the aqueous phase and also prevent droplets coming together due to attractive forces if you don't have enough charge, and also causing coalescence and phase separation. So fluctuation, coalescence, phase separation. Protein needs to be soluble. If it's not soluble, again, it won't be, it would just probably aggregate and fall out and not be able to interact with the water phase or enhance the viscosity in the continuous phase if the water is continuous phase. The conformation of the protein, is it an open structure protein like casein, or is it a globular protein like whey that requires denaturation to unfold and be able to emulsify. Okay, so here's the theory that tells you open structure, flexible, like casein, are very surface active. So they have high adsorptivity at the interface and very high flexibility because open structure. Globular proteins are less surface active. They require a little bit of a push to denature them and provide this balance on the surface of that protein. So usually they're less surface active unless we prompt them to be. And they are usually smaller. Even if they unfold, they don't unfold completely and be an open structure like casein, for example. So more proteins will get on that. There will be more space for the protein to form around the bubble or the droplet. They form thicker films. So a combination usually of these characteristics forms a very nice emulsion at lower concentration and a stable emulsion. So combination of different types of proteins and conditions will get you to a point where you have good activity, good emulsion, small droplets, and stable. The thicker the film around your oil droplet or water droplet, the more stable it is. Um, Extrinsic characteristic, again, temperature, we need to induce some denaturation sometimes. pH and salt impact the charge on the surface of the protein. So you want to find that not excessive charge. They won't interact, they won't form film, and not a lot of salt that would shield charges and will cause aggregation, and rather than a nice balance between water interaction and protein-protein interactions. And homogenization is important to reach to the droplet size that would be enough to cause stability over time. Larger droplet size, you have more or less distance between droplets, so flocculation, coalescence, and phase separation. So droplets come together and then coalesce, and then we get phase separation. Sometimes adding surfactants can destabilize the proteins in the film on the surface because they are small molecular weight. They can replace or easily go to the surface, displacing proteins. So we have to be careful how much we want to help stability, but not just destabilize the protein films. So processes that impact emulsion formation and stability. So you have the rate of adsorption at the interface, how quickly the protein can reach the interface, how much protein get absorbed at the surface, because if you don't have enough protein absorbed at the surface, you form thin films that are not very stable, how much conformation rearrangement we need. So if you have a protein that is very rigid in structure, a lot of disulfide interaction, it's not denatured, you don't have that conformation rearrangement that you need at the interface. So when you have conformation rearrangement and then this or reorientation, you reduce the surface tension, and this is important. And then the ability to form that protein layer, cohesive protein layer. So you need to form protein-protein interaction. So everything is a balance. You need to have some charge, flexibility in structure. You need the protein to interact with another protein to form the film, but you need enough charge to repel proteins on a surface of one oil droplet and then protein on the surface on another. You want to have enough charge so that they repel each other. So that is very important in balance of everything, kind of. So emulsion stability can be measured in terms of phase separation, and what leads to phase separation is changes in the droplet size over time. So that's here we illustrate what happens when you get fluctuation. So the droplets come close to each other, then they open and form larger bubbles, and then gradually more larger bubbles coalescing cause that phase separation. Depending on the components of the system, sometimes we see creaming at the top or sedimentation. It depends on the density and what components are in your emulsions based on density separation. A lot of factors impact the stability of the droplet size. We talked about that. Difference in density between the two phases and the viscosity of the continuous phase. If you have a little bit more viscous continuous phase, the droplets are kind of more stabilized. If you have a very thin continuous phase, and you just have more movement, that would bring them together because you don't have that viscosity that holds them apart. So if we want to look at it in terms of an equation, so the V is the rate of creaming or separation, rate of separation. The R has to relate to the radius of the droplet. And then G is the gravitational force. And then the delta P is the difference in density. You see those all are directly related to the rate of separation. So if you have larger radius, means bigger droplets, then the rate of separation is larger. If you have higher gravitational force, rate of separation is high. If you have greater difference in density, you have higher rate of separation. Now the mu here is the viscosity of the continuous phase, and it's inversely proportional to the rate. So the higher the viscosity of the continuous phase, the lower is the rate of separation. Sometimes if you have soluble protein that is not at the interface, it increases viscosity and it helps with stabilizing the emulsion. So large protein with high gelling ability can form strong viscoelastic protecting film. Dissolved proteins can add to the viscosity of the dispersive phase. And now let's give examples about caseinates, soy protein, and pea protein. Caseinates are open structure proteins. They're very amphiphilic, so they are amphipathic. So amphiphilic, amphipathic. So it means they have clusters of hydrophobicity and clusters of hydrophilicity, which makes them an open structure because of this proline secondary structure breaker. So they don't form globular protein. So they are natural emulsifiers. So the 0.5% protein solution of sodium casein have a really high emulsification capacity, which emulsification capacity stands for the amount of oil that can be emulsified by 1 gram of protein. So it has 1 gram of protein of caseinate can emulsify 1,800 grams of oil. So if we look at soy, we need 1% protein, more protein in there to cause the emulsion to form, and you have an EC between 1,200 to 1,500, depending on the source of the protein. Whereas pea protein, you need more protein in solution to form an emulsion, 2%, and you get a very low emulsification capacity, again, depending on the source of the protein. Here in this example, 400 grams per gram. So different protein sources, different characteristics, different abilities to form a strong layer, to reduce the surface tension, and to form stable emulsions. Yeah, and here just to illustrate how globular proteins, especially plant proteins, they're large, they're globular. We really need to work them, make sure that they move to the interface and open up and form this layer around the droplet. Okay. So So how do we measure emulsification capacity? We form an emulsion using an homogenizer. So the way we form the emulsion is we prepare our protein solution and we titrate oil and we homogenize until an emulsion is formed, but we keep dropping oil at specific rate, constant rate, and homogenizing. So the emulsion thickens and thickens, but at some point we added more oil than the emulsion can hold, and the emulsion breaks. So this is an inverted emulsion or broken emulsion. We stop titration, we measure the amount of oil that we were able to emulsify, and we calculate the amount of oil. We convert volume to mass using the density of the oil and determine how many grams of oils were emulsified by a gram of protein. There's another assay to measure emulsion stability, but this assay is very predictive that does not have a strong predictive power. So we put reagents to cause a break of the emulsion in a short period of time, and we measure turbidity over a specified time. It gives us a prediction of the stability of the emulsion, but usually this is not what we should use to determine stability of real emulsion systems. So we form emulsions and we measure droplet size. And then what we do is we measure droplet size over storage. So we store the emulsion most likely almost always under accelerated shelf life so that it's not a very long study. And we look at increase in droplet size over time. We measure turbidity as well. We measure changes in charge to see what's causing the drops to increase in size due to fluctuation and coalescence that happens in time. And different proteins treated differently, either they stay stable or we see a change in droplet size over time. And again, here with microscopy, here's the example of the cheese, again, with looking at the droplet sizes over time, but we did it with pea protein emulsions pre-protein treated under different conditions. And we looked at a commercial protein and our treated protein, and we looked at aggregation forming over time. So we see that the treated protein under specific conditions, the emulsion stayed stable over time, whereas the commercial protein aggregated over time. So we combined microscopy with the measurements of oil droplet size changes over time, viscosity, turbidity, and charge. So that gives us a better evaluation of emulsion stability than just doing that model system assay, which is not a very good predictor. So last here we have the foam. So a foam, in this case, you have the protein interacting with the aqueous, and then you have, or the aqueous, or it can be lipid as well, a fatty layer, where you have a mixture of aqueous, fat, foam, and air, that is. And the protein tries to orientate itself in a way that provides stability around the air bubble. So the dispersed is our air bubble, gas phase, and the continuous is either liquid or solid. We have, again, the protein forming the different steps to form, again, a film around the air bubble. And it happens by mechanical whipping or injection of the air or gas. And many food structures are really foam. And these are a couple of examples. So whipped cream, obviously, angel cake, meringues, souffle. Ice cream is a foam and emulsion. So Again, the foam stability is determined by so many factors. One is how thick the protein layer is and how much repulsion you have between two bubbles. So the surface, the protein, and the surface here, how much you have repulsion happening or disjoining pressure due to charge, for example. And then here you have the continuous phase, and you always have this thinning of that phase that might cause those bubbles to coalesce. However, the viscosity of the continuous phase helps the bubbles stay separated longer. So instead of the liquid draining, um, it slows down if the viscosity is a little higher. Um, And this is exactly what I just said about the disjoining pressure. Measurement of foam, we measure foaming capacity and foaming stability is that you form the foam and you measure how much volume difference you obtained. So basically, per gram of protein, how much foam was generated. So we can measure the overrun volume of the foam minus the volume of the liquid after you form the foam. So volume of the foam after the foam is formed, volume of the initial liquid before you form the foam over the volume of the initial liquid. So, or we can measure the foam volume that is generated, and we go per gram of protein, milliliter of foam per gram of protein. So either that or overrun. And then the change in foam volume over time, that gives us stability, how much volume of foam we lost over time. Okay, and I think that's it. And now we talked about intrinsic factors, extrinsic factors impacting protein structure. We talked about these functional properties and how structure impacts function. So we talked about, we gave you a few examples of structure-function relationship. So I think now next we'll be talking about completely kind of a separate topic, which is enzyme application of enzymes, because enzymes are proteins, so it's good to talk about that. And then we start talking about proteins, different protein sources, dairies and legumes and cereal proteins. So that's it. I'm going to stop sharing, and I will have to look to see how much time this lecture took, and I will send you an email about it. Okay.